Thank you for coming along. It is a real privilege to come and have a chat with you. It is a long ways from Australia to Vilnius, 34 hours from tarmac to tarmac. So please return the favor and come visit us in Australia at some point. So today I'm going to try to give you a rundown of the entire universe. It's a mixed audience. So I'm trying to cover everyone from physicists to people who maybe are future physicists. So I don't guarantee everything's going to resonate with everyone, and I'll try to lead you through where say, just take a moment while I explain this for the physicists in the audience. But it's good, I think, to get a sense of how a physicist sees the world, even if not all of you will understand some of those aspects. So let's start at the very beginning of cosmology, and to do that, we need to think about how we measure things in cosmology. And Edwin Hubble, who had access to the world's largest telescope, the Hooker 100-inch telescope that's still on display outside of Pasadena, was able to measure distances to objects. And you can measure distances to objects by looking at how they appear. The further away they are, the fainter they appear. And so you can literally judge the distance, relative distance at least, by looking at how bright a star is in one galaxy, seeing how bright that star is in another galaxy, and comparing how bright they are. It goes as the square of the distance, the faintness does. The other thing that happened that Hubble didn't do, but he borrowed work from Vesto Slipher, was to look at the motion of the galaxies. So Slipher went out and looked at all the nearby galaxies and looked at their light and saw that the light of these galaxies was stretched almost always redward. Now, if the objects were coming towards you, it would be blueward. If they're going away, redward. So it was a mystery in 1917, 1916, when he made these measurements, of why essentially all of the galaxies he looked at were moving away from us. Hubble put that together when he measured the distances to these objects and produced this diagram in 1929. So this diagram shows essentially the distance measured by how bright stars were in galaxies. So he assumed essentially the brightest star in a galaxy is always the same brightness. Now it turns out that's not strictly true. It's actually not even very close to being true, but it is true enough so that this was not a ridiculous measurement that he made. So he measured distance by how bright the objects were. He measured the redshift that Slipher measured, that is how much the light had been stretched by what they presumed was motion in the y-axis, and you can see the further away you are, the faster you appear to be moving. And from that, Hubble announced to the world that the universe was expanding. Now watch that diagram. I'm going to expand the universe in this cartoon, and I'm going to overlay the beginnings and the afterwards, before I expanded the universe and after, from our position. And what you can see is that nearby objects in this cartoon have moved a little bit. If I was measuring their velocity, it would be low. Distant objects, well, they, on the other hand, have moved a lot. Their velocity would be high. So this cartoon sort of gives you a sense that if the universe is expanding, you see what Hubble saw. That is, the further away you are from your reference point, the faster the object is moving away. So we, of course, don't just use cartoons. We'll eventually get to a theory, but I want you to think about, as a thought experiment, if the universe is expanding, let's run the universe in reverse. What happens? Well, when we look back in time, things are closer and closer and closer and closer to everyone, so that everything at some point is on top of everything else. The idea of the Big Bang naturally arises if the universe is expanding. You run the universe back in time and everything's on top of itself. So, how do we think about this? Well, the Big Bang, if you put it as a graph, and I'm going to do a very simple graph of our cartoon, the distance between two galaxies starts where the galaxies are on top of each other, and they move to where they are right now. And so that dotted line That slope of that line allows you to essentially run the universe back in reverse. So if I can measure a distance to a galaxy, I can measure its velocity or its redshift, then it turns out the slope of that dotted line is the ratio of those two numbers. And I can just run the universe back in time, and I can measure how old the universe is by simply measuring what Hubble did. We call that Hubble's constant. That is the ratio of a galaxy's distance divided by its velocity. And if you go through and do this, you can get an estimate. And that turns out what I did for my PhD. So if I take you to 1993, yes, that is me as a 26-year-old with my PhD supervisor measuring the expansion rate of the universe. And what did I get? Well, the universe is about 14 billion years old. It's uncertain to about 10 or 15%. And it turns out that's more or less the correct answer, that as we've refined the measurements we've zeroed in on, I would say I do not get credit, nor should I, of providing the definitive answer for the expansion rate of the universe. That was done over many decades, getting more and more precision. I was part of that conversation, and indeed that's how I got my job to go to Australia, because the head of the Australian National University's astronomy department was leading the Hubble Key project to measure the Hubble constant. And so my value of the Hubble constant, as I said, is more or less within the range of the uncertainty, which was great. Now, we've been in cartoons so far. The hard reality is we actually have to have a physical model, and that physical model comes from Einstein. Now, Einstein in 1907, 2 years after his great year of doing the thing that he won the Nobel Prize for, which of course was the photoelectric effect. He also did Brownian motion in 1905, and he did special relativity equals mc squared, all in 1905. 2 years later, he supposedly, and this is probably a made-up story, but I like it nonetheless, Einstein said he saw someone fall off a roof. And as they watched the person fall, presumably to their demise, rather than saying, I need to go get an ambulance, he said, I think that person must feel weightlessness. I think his acceleration must directly counteract gravity, so he doesn't feel it. Then those two things are equivalent. They're interchangeable. The equivalence principle, that moving faster is exactly the same as gravity. Acceleration and gravity are interchangeable. Now, it doesn't sound like okay, fine. Well, it turns out it took until 1915 for him to reconcile the fact that you cannot tell the difference if you're in an elevator on Earth that is, forget what's not using a box on Earth, or you're on a spaceship. One feeling gravity and one moving faster, okay? Those are equivalent things. And so he, after all this time, in 1915, published his work in November 1915, and it predicted many things. It predicted that space was curved. It allowed Einstein and others to do a whole bunch of things, cosmology the first time, as I'll talk about in just a second. And it is when it was realized this was correct, as I'll show you in the next slide, this is the thing that actually made Einstein a household name. Not equals to mc squared. 1905 made Einstein a very famous physicist to physicists. This is where he ended up on the front page of the New York Times, the front page of the London Times, because he thought from thought itself, seeing the person fall, he thought up a whole new revolution and changed Newton's laws of gravity forever. And as I said, you have an idea, you got to test it, and that testing came from looking at an eclipse. The eclipse blocks out the light of the sun. You can see stars. The sun has gravity. Gravity will bend space, so the stars will not be where they should be in Einstein's theory. And you can make a prediction where they should appear. You wait a few months, the sun goes away after the eclipse. You see where those stars are, and you compare. And it turns out the answer you get is exactly what Einstein's theory of general relativity predicted. So, Einstein's theory of general relativity, as I said, allows you to do all sorts of things. It's a very complicated theory, all right? It is a theory that has to reconcile a whole bunch of things to do with time and space. And it turns out that involves, for the physicists and the things, roughly, depending on how you think about it, 16 nonlinear equations that are coupled that you have to solve simultaneously. Okay, turns out that's actually quite hard, unless you make some assumptions. Now, one of the assumptions you can do, which is beautiful for cosmology, is what we call the standard model assumption, which is that the universe is homogeneous. That is, every part of the universe is like every other part of the universe to first order on large scales. And it's isotropic. That is, there's no preferred direction. Everything and every direction are identical. And if you do that, then those horrific 16 nonlinear equations break down to two equations known as the Friedmann equations, one of which is this one. This is a differential equation. And for the physicists in the audience, if you're not a physicist, we're going to take 3 to 4 minutes of doing some stuff in a physics way, and then we'll move on and you won't need to know too much more about it. Speed of light is c. A is the relative size of a piece of space. So it turns out there's dynamics, and space changes size, and you need to worry about how big a piece of space is. And so this equation, A, tells you how big a piece of space is over time. So if a piece of space is, for example, has a unit 1 now, then this will tell you is it a half or 2 in the future or the past, okay? T is time, 8 pi, I think those are just normal numbers. G is the gravitational constant. Rho is the density of the universe. A, again, is the scale of the universe size. And K, it turns out it's curvature. Now, as indicated, one of the nice things about A, the scale of the universe, you're like, why are you doing that? And it turns out it's really easy to measure because light traveling from galaxies gets stretched if the universe expands, and we can measure the wavelength of light to 1 part in a million if we want to. So we can actually measure A from a distant galaxy because the light is being stretched to 1 part in a million if we need to. Okay, so we have a way of tracking the relative scale of the universe by how a photon is perturbed as it travels from a galaxy to us. So, curvature. Space can be curved locally, where you kind of put a little divot in how light will travel, but globally it can be curved as well. And so, depending on how much stuff there is in the universe, there is this constant k that tells you, is the universe essentially hyperbolic, that is k equals -1, where triangles add up to less than 180 degrees in this universe. It's a saddle-shaped universe that goes on to infinity. A heavy universe, k equals +1, where the universe literally bends onto itself, so it's finite. It's a universe, if I head out this way, eventually I have time, and if I have enough time, which turns out you don't, but that's another story. If you head out that way, you'll come back to where you started, just like you would on the Earth. Earth has a k equal +1 geometry, it turns out, in the same way. And then there's the k equals 0, what we call flat or just right, where the universe has exactly the amount of stuff so that triangles add up to 180 degrees. Now, the thing that determines your geometry is your density. If you are above the critical density that gives you just right, you're heavy, and space, the gravity bends space onto itself. If you're lighter than that, then space is naturally springy and springs away from itself. Okay? This all comes out of that crazy Einstein theory of general relativity. And you can go through and solve that differential equation. That's what it looks like. I don't care. I'm going to show you what it looks like on a graph, which we can all understand. So this is this relative size of the universe. This is time. Now imagine I have a universe that has nothing in it. Density is 0. Okay? then the scale factor of the universe, well, it just gets bigger and bigger. It starts, just coasts along. So it's essentially like throwing a rock in space where there's no Earth. It starts and just keeps going for all of time at that same velocity, same expansion rate, just gets bigger and bigger over time, okay? Now, if I have a universe that has less than the critical density, and I've just given you a term omega there. Omega is 1 when you have a critical density equal to 1. Okay? In this case, the universe has gravity. The gravity slows the universe down over time. So the universe, after the Big Bang, slows down. You'll note that my extrapolation is going to be a little wrong when I measure the Hubble constant and give you a distance. And it can slow down for all time, but it turns out it asymptotically reaches a value, or it essentially never, ever quits slowing down until you have a density, if you're born with a density where omega matter is greater than 1. That is, you're above that critical density. Space is, of course, finite and wrapped onto itself. That is a universe that slows down quickly, actually stops expanding, goes in reverse. All universes begin with the Big Bang. Only the heavy one begins with or ends with the Ganab-Gib, the Big Bang backwards. Okay? So let's a review. If your density, okay, is 0, universe just coasts. If you have a bit of stuff in it, the universe slows down because gravity slows the universe down. If you've got a lot of stuff, the universe not only slows down, it will start to contract and end. That was the state of the universe in 1994 when I started my project with a whole bunch of other friends around the world, was to figure out which of those curves we're on. Okay? Now, there's some things we need to also worry about, again, for the physicist. The universe can have other stuff in it than what I talked about. It can have material like photons. It can have things like neutrinos. Or it can have things we don't even know exist that behave differently than we do as the universe expands. Okay? And it turns out you have to worry about these things, and we call that they have in a gravitational equation of state. And for this audience, I want you to think about a photon. If I've got a photon in a box, it has a wavelength. As the box stretches, expands, the photon stretches. That's what gives me the redshift I can measure to 1 part in a million. But if I've stretched the photon, it turns out it has less energy. So that box has gotten bigger. The photon has lost energy. If we're in that box, we're just an atom in the box. Our energy stays the same. That is, E equals mc squared for us does not change. So there is a difference between a photon and an atom in a box that's expanding. And it turns out that affects how the universe expands. Okay, I'm not going to say too much more about that, except for I'll show you some graphs later on, because it turns out it's important. All right. The other thing to know, this is almost philosophy, is that if you have a bunch of things in the universe, they all add up together to tell you how much stuff there is in the universe. So I got to add photons, and I got to add atoms, and I got to add neutrinos, and I got to add anything else that's in the universe. They all sum together to tell you the geometry. It turns out in general relativity, photons and atoms push on the universe differently gravitationally. Okay? So we're going to have to keep those things. And perhaps not a surprise, if the universe is geometrically open, that means it's infinite. It was infinite when it was born, and it was infinite when it dies. You don't make something that's infinite finite. Okay? In the same way, if the universe is closed, that is, if the universe is heavy and wraps onto itself, is finite, it's always finite. You don't say something finite, infinite, except for in the infinite amount. It takes an infinite amount of time to make something infinite. All right, I'm going to skip this. you can actually write this down as a set of equations. This is the actual equation we write down and we solve when we make our measurements. That's me going, see, this is what we really do. Let's not worry about it. Let's get on conceptually and think. So if you've just checked out, you can check back in now. We're going to go and we're not going to talk too much math for the rest of the bit, but I just wanted to show the physicist what's under the hood. All right, so we're going to measure the universe's past. So think about a universe as it looked in 1994. The universe might be essentially empty. There might be almost no mass relative to that critical value, which means that the universe doesn't slow down over time. It's going to coast forever. It'll just get bigger and bigger forever and ever. That means that if I look into the past, how am I going to look in the past? I look at a really, really distant object. Its light travels to me at the speed of light, 300,000 kilometers per second. And if I look far enough away, 1 billion light years, I'm looking 1 billion years into the past. I can look 5 billion years into the past. I can look 8 billion years in the past. Then it turns out in 1994, I couldn't look any further in the past because the telescopes weren't big enough, because the things got too faint. But in 1994, we knew with the new telescopes, the Keck telescope, the Hubble Space Telescope, we could look about 8 billion years in the past. And during that time, we could see whether or not the universe was changing its rate of expansion. I could measure the distance to an object, to a galaxy. I could measure its velocity, and I could essentially just see what that expansion rate looks like back in time. Now, I knew the universe has something in it, so it's got to be slowing down a little bit, right? So the real question we were trying to answer was gravity winning? That is, that dotted line is the trajectory our universe takes if the universe has just the right amount of material so that space is flat, okay? If it is slowing down faster than that dotted line, gravity is 1, the universe is finite, it has a beginning and an end. Other side of that dotted line, gravity loses, the universe is light, the universe goes on forever. So that was the experiment we pushed in 1994. And the reason we could do it was because my colleagues in Chile had gone through and figured out how to measure the distance to a type 1a supernova. These are stars that explode very rarely. The last one seen in our own Milky Way, which has got almost 1 trillion stars, was in 1604. It was observed by Kepler and by Galileo. We haven't seen one since. But these things, we believe, are, if you know what a white dwarf is, we believe they're the thermonuclear detonations of white dwarfs. I'm not going to talk too much about them today because it's lack of time. But they characteristically take about 18, 19 days to reach maximum brightness. They fade away then over the coming months. And the beautiful thing is they're 5 billion times brighter than our sun. They synthesize the iron that you are sitting on, which, may I say, has come to you via China and Australia. So that was the stuff you're sitting on almost certainly was dug out of the ground in Australia, put together in China, and shipped here. Okay? But they were produced by these exploding stars 5, 10 billion years ago. So these objects, my colleagues in Chile, shown here, went through and they did a really great experiment where they observed these things for the first times across the sky, calibrated how bright they were very accurately, and demonstrated you could measure distances to these objects to about 7%. Now 7%, okay. For astronomy, where we're used to factors of 2 being good, 7% was like a new world. It changed the world. It was like AI, right, of the time. So this work enabled us to go through and make a measurement that we just could not make otherwise. And here I am with Nick Sunsef in Chile as a young person talking about how we're going to do this experiment. And what we needed to do was to find these very, very rare objects. Now, one of the things that people always ask me is, why do we do astronomy? And the answer is because it's cool, but it's also very useful. So we had digital cameras that were in this case, 4 megapixels, and we'd put them together into sort of 8 million by 64 megapixel cameras. We had those in 1994. Okay? That technology has transferred through various incarnations, including the CMOS camera that I'm being filmed on right here, which is directly from a space probe mission to Jupiter, a CMOS camera. But this data came in when the fastest computer in the world that I had access to, I won't say the world, but the fastest computer I had access to was 100 times slower than my iPhone is. We had 1 gigabyte hard drives. We took 50 gigabytes of data. So I literally had to kind of daisy chain 50 computers to chew through this data at a time when there was no software to do it. And what we had to do was find the needles in the haystack, because we would take over 1,000 images like this a night, and I'm only showing you a tiny amount of the resolution here. But in these images, there will be supernovae, 3 of them, in an entire night's worth of data. And we know them because we take images before and after, and we have to figure out what's changed. Now, this is all pretty reasonable these days, but all the software I had to write as a young postdoc. And I'll be honest, I was not a great code writer. I was fast and dirty. Now I'm just dirty, I'm not even fast, but anyway. And you can see a little smudge of a galaxy and an object next to it. And as I said, we take an image a couple weeks beforehand, and we can see where nothing has become something. That object, the supernova, turns out was 5 billion light years in distance. It exploded before the Earth was formed, traveled through the universe, and landed smack onto the Saratoga 4-meter telescope where we discovered it. Okay? So that allows us to measure its distance. Turns out it allows us to measure its velocity. And we can do this many, many times. So let me take you to the results that we got after 3-4 years of hard work. Each of our distant supernovae is a measurement on this. We have nearby objects. These are largely done in this part of the diagram in the nearby universe. We're within 1 billion years. And you can't really tell which trajectory the universe is on. But when you go through and look at the very distant ones, the first thing when we looked at those, each object has essentially an uncertainty shown by the error bars, the whiskers, as is sometimes described. And you can see that not a single object is consistent with the universe, even with the uncertainty of the universe slowing down, so that it stops expanding and goes in reverse. So I have to admit, when I first saw this, I was like, oh, I kind of like that. I like a universe that had a beginning and an end. It seemed good. Universe doesn't care what I think, it does what it does. Okay? But when you analyze, you can see every single object is actually not in the gravity loses part of the diagram, it's above the line. And while some of the uncertainty is below the line, on average, when you average it up, they're actually quite definitively above the line. You're 99.95% sure they're above the line on ensemble. Now, as Christina talked about, when we saw this, we didn't go, woohoo! We said, oh, we have done some horrible mistake. And we spent not a couple weeks, we spent several months working as a big team trying to figure out what we could have possibly done wrong. But the fullness of time showed we hadn't done anything wrong, and as we did not know, but we were in competition with the team out of Berkeley and the rest of the world, and they were getting exactly the same answer. So the universe seems to be expanding slower in the past and had sped up. The universe is accelerating. All right, so this is what it looks like in terms of what we think the universe is doing. I'm going to talk a little bit about that later, but I will leave that for now. So there were 2 papers done by these 2 teams that had competed, and yes, we were in Stockholm together in 2011. And so we celebrated and kind of buried largely the hatchet of competition from that time. So how do you make the universe accelerate? Well, it turns out Einstein's theory of gravitation, general relativity, I talked about that you can have things that behave differently in space. And Einstein, when he started looking at general relativity, he did not like the fact that his solutions to the universe seemed to show the universe in motion. It had that term of A, the scale, change. So he created a fudge factor, which turned out, he said, oh, that's allowed to be in there. It's a kind of a nuisance and a complication, but it's absolutely allowed to be there, which he called the cosmological constant. It is the energy of space itself. So if you ask yourself, if I have a piece of absolutely empty space, what is that? Well, at first order, nothing. But it turns out actually you got to allow it to have energy. That every piece of space actually has energy. That turns out to be the cosmological constant. But he thought, well, okay, so gravity, when I put this in my equations, this cosmological constant, it turns out pushes gravity away. So it, he thought, could balance the retraction of gravity and balance the universe out so it would be static. Turns out it doesn't work. It's unstable, which means that if a butterfly flaps its wings on the other side of the universe, the whole universe goes into motion, okay? So actually what he described in life as something he thought he regretted, his big regret in life, the cosmological constant, is the thing we seem to have discovered, something we call dark energy, because we're not absolutely sure it's as Einstein described. So dark energy, something that, like energy tied to space itself, spread all over the universe for all time, doesn't change. That turns out it gives us the acceleration we need. Almost the only way we can get the universe to accelerate. All right, so our analysis at the time showed that the universe needed to be about 30% stuff like us with gravity that's pulling, 70% stuff pushing like the cosmological constant. All right, seems a little crazy, but the first thing you have to think about is, well, what does this mean? Well, that is what the curve of Einstein's theory tells you such a crazy substance would do. The universe continues to accelerate exponentially in the future. In the future, it turns out, because the universe gets bigger and bigger and our density drops as the cube of the scale factor, right? Because you get more and more volume and we don't change, we become irrelevant in the future, and the entire universe is dark energy. It's the only stuff that matters because it is part of space itself. And when you double space, it's still there. You triple space, it's still there. We become less and less and less. But it also means in the past that it wouldn't have been relevant, because in the past, when the universe was smaller, our density is much higher and its density is the same. So it makes this very peculiar curve where the universe in the past was slowing down and only recently started to speed up. That's something we can go predict, okay? We also want to look at this from other ways. And a great experiment is this image of the entire sky, which is the afterglow of the Big Bang, the cosmic microwave background. Everything you see in there is a sound wave left over from the Big Bang. And yes, space can have sound waves. They're just very, very long waves. And so it turns out we understand sound waves really well, and you can throw a rock in a pond, think of the universe as a pond, and the wave action depends on what the pond's made out of. If it's made out of honey, the waves look different than if it's made out of water. So the Big Bang, turns out, was like throwing a whole bunch of different sized rocks into the universe. You let the wave action kind of go boom, 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 and you can actually reproduce, theoretically, what we see in the sky. There's a galaxy, which we remove. And so what do we predict? Well, it turns out we predict how many sound waves there are of different size. So these are great big sound waves. These are very small sound waves. And the y-axis is how many of them there will be. So the models predict that there should be a bunch of medium-sized sound waves here, and then kind of some weird bumps and wiggles. And what the universe is made out of, turns out, determines what those sound waves look like. And then you can look what the data looks like. And it turns out, amazingly, we can predict with simple acoustic physics exactly what the Big Bang sound waves look like. Not just a little bit. You can see the data, you can see the curve. I mean, when you fit something like that in physics, you know what you're doing. And it turns out the best fit says that there's something in the universe called dark matter. That is stuff that has gravity, just like you and me. I've got my voice back. But this stuff has got a funny property. It goes right through itself. It goes right through us. It goes right through the Earth. It goes right through the sun. It does not interact, but it has gravity. And it turns out we've seen evidence that there is invisible gravity throughout the universe, and we always find there's a lot more of it than us, okay? And this data without dark matter just simply does not fit what we see, but with it, it fits exactly what we see, okay? It turns out that dark matter, we suspect, might be an undiscovered particle, but at this point, we haven't been able to find it. The cosmic microwave background sound waves also allow us to see acceleration indirectly because we can actually measure the shape of the universe. The universe is, when it's bent, essentially magnifies how things appear relative to a flat universe. And so, for example, if you look on one side of a spoon, the closed side, you're bigger. If you look on the other side, you're smaller. If you're just right, you're somewhere in between. And so as a graph, it looks something like that. And so you can predict the curvature of space by how big those sound waves look. And it turns out when you do that, they're exactly consistent with a universe that is flat, that has just the right amount of stuff in it, so that the universe is not too heavy or too light, to like within 0.5% and even 0.1% these days. So what does this mean? It means that if you go through and look at how much dark matter and normal stuff there is, 30% of the universe has got gravity in this experiment, and 100% of it has to add up to just right. So that means there's got to be something we're missing, mystery matter, the same mystery matter that we see causing the universe to accelerate over time. So any way we look at it, we get a picture more or less like this, that the universe is 70% stuff that's pushing, 30% stuff that's pulling, but only 5% of the universe are the atoms that we know here on Earth. 95% of the universe are things that we've never been able to detect here on Earth. Now, you might say, if you got to make up 95% of the universe, you probably don't know what you're doing. And that's sort of true. But it turns out science is about making predictions with your theories. This theory has predicted pretty much everything we've thrown at it. And when you look at that cosmic microwave background, it is almost impossible to imagine how you accidentally fit something like that without having something pretty close to the correct answer. So it's a messy universe, but it is the story we keep seeing. We take more data. This is what supernova data looks like these days. Thousands upon thousands of more data. It turns out it more or less exactly gives the answer we got in 1998, except for there's just where we have the worst data in here, there might be a small deviation indicating that the acceleration is not exactly like Einstein's cosmological constant. Another experiment we can do is we can take these sound waves, because these sound waves become the galaxies of today, and those sound waves are imprinted in the galaxies of today. And so by looking at literally hundreds of millions of galaxies, we can reconstruct the sound waves of the Big Bang and use that scale to connect just after the Big Bang, when those sound waves are imprinted in the sky, to the present. And so the big sound wave is shown and how big it appears at different times back in the past. And again, in the same sort of not too distant part of the universe, there's a small deviation. a deviation indicating it's almost exactly what we said in 1998. Einstein's cosmological constant is correct, but there's a slight deviation of a couple percent. Now, at this point, not everyone, including myself, is convinced that this is what's going on. These are really hard measurements to make, but there is just a little bit of an idea, maybe something's not quite the simplest idea we had in 1998. We're taking more data, we'll know more in a few years, but at this point, I will say maybe it's not the simplest solution, but we need more data. Now, it turns out there is, this is a physicist's way of going through and essentially looking at what the dark energy is. I'm going to skip it. But there's one other thing that's not quite right that I think is more convincingly not quite right. When we measure the Hubble constant, like I showed you I did for my PhD thesis, we've gotten better and better at doing that. Adam Rees, who I won the Nobel Prize with, has been working very hard with the Hubble Space Telescope to do this more and more accurately. The cosmic microwave background, those sound waves, allow us to measure the Hubble constant really accurate back 13 billion years ago. And because they're so accurate, we can project that to the present. And when we do, we get an answer that deviates quite distinctly from what we measure in the nearby universe. That is the cosmic microwave background measurements and the nearby measurements of the Hubble constant, the rate the universe is expanding, disagree by about 8%. We don't know how to reconcile that. It turns out theoretically, they're very difficult to reconcile. I'm working on a completely new way to try to measure the nearby expansion rate, to measure it much more accurately. Actually, the same way I did in my thesis, just using modern techniques. And we'll see, but I genuinely believe we have a problem here. Now, in physics, when you have a little problem, physics is an exact science. And when you have a little problem, it's a big problem. It means something is wrong, because physics is all about predicting things exactly. So 8%, 1%, 1 part in 10 to the 9. If you can measure it that accurate and you get a different answer, there's something broken. I have no idea what's broken. I just know there's something broken, which is good. It means I still have things to do. I'm not going to retire out of boredom. So figuring this out, I think, is going to be really important. I have no idea what the answer is. So there's lots of questions, it turns out. This is called the Hubble tension I just talked to you. Is it real? Some people would say, oh, it's so hard theoretically to solve it. You guys are just wrong. So we as observers need to go out and make a really good measurement of that. What is dark energy? Is it changing over time? I've shown you maybe it is, but we're not sure. But then there's some other questions I haven't even talked about. Why do neutrinos have mass? It turns out the standard particle theory does not have them having any mass. The standard particle theory of particle physics also doesn't tell us why we exist at all. It turns out the atoms should have disappeared right after the Big Bang into a puff of light. And finally, the thing I haven't talked about, but the thing that throws the rocks into the universe right after the Big Bang, is where the universe expanded exponentially, like it seems to be now, in something we call inflation. We don't really understand. That's just a cartoon we sort of make up. We don't understand it. So there's a lot to do. And there's all these things to do in astronomy proper, like understanding how the universe evolves from the Big Bang to the present, which is what we're working on right now with the James Webb Space Telescope, taking amazing images like that where we can zero in by how really red objects whose light's been stretched a lot, like that one, which occurred only a couple 100 million years after the Big Bang. This is the most distant object known in the universe. Its light has been stretched by a factor of 14. It is a much bigger galaxy than we would expect to be there. It's kind of strange. Its stars maybe not quite what we expect. There may be a whole generation of stars right after the Big Bang that are unlike the stars of today. I don't know. Some interesting things to think about. And we're going to be able to see more and more with the next generation of telescopes, like the European Southern Observatory, ELT, and the Giant Magellan Telescope, both going to be in Chile. And we use these things to use these amazing computer simulations we can do now to build galaxies in a computer and see what they look like relative to what we actually see with telescopes. And so this is rapidly changing part of our field. We're going to be able to observe in radio frequencies because gas, cold gas, before there are stars, emits hydrogen, emits radio waves. So we literally should be able to go back and see the universe when it's just emitting cold hydrogen, and then it's going to get chopped up as stars form, destroys the cold hydrogen gas, and we're going to see the universe go from being empty, without life, to suddenly turning on. So that's what the Square Kilometre Array, which is based in South Africa and in Australia, is seeking to do. Finally, people always want to know, black holes, they're clearly real. There's so many of them, it turns out, and we can see them directly through gravitational waves predicted by Einstein's theory of general relativity and seen in these experiments where we look at space, the size of an atom, go like that, which is what a black hole, when they merge together, they create a ripple in space that we can measure. So it turns out when we measure these things, there are all sorts of black holes merging, and they're really big. And this is one of the clues that I think that the first generation of stars maybe were different. They probably were big, and they probably did not explode as supernovae, which we think most modern stars do, but collapsed down and formed very large black holes. And we can see these black holes grew into giant monsters 1 million times or 1 billion times the mass of our sun by making telescopes at radio wavelengths the size of the Earth. And these are real images of a supermassive black hole in a nearby galaxy, and it is more or less what you predict from general relativity they should look like. You can actually see the shadow. You're not seeing the black hole. You're seeing where the black hole doesn't allow there to be any light because it kind of zeroes out that part of space. Finally, we can ask questions about planets. This is Venus going in front of the sun, and it turns out these transits are very useful for understanding exoplanets because they give us very specific information. And we have found literally thousands upon thousands of planets up to now, and we will find more with future missions. So this is the current catalog. You can see more than 6,000 there not too long ago. This is a picture of Venus in front of the sun. And you can see there's a little rim of light. That's because the sunlight is going through Venus's atmosphere. And as it goes through Venus's atmosphere, it picks up the chemical fingerprints of Venus's atmosphere. Now imagine we're not looking at Venus going in front of the sun. Imagine we're looking at an exoplanet going in front of its sun. Those same fingerprints are going to be picked up. So with, for example, the European Southern Observatory's ELT, we're actually going to be able to pick up the fingerprints of stars, planets, when they go in front of them. And to show you why that's important, here's a spectrum, the colors of the rainbow spread out. Each dark line there is a fingerprint of a various atom. We have hydrogen, we have sodium, but way up in the corner, we have something not in the sun. It turns out our atmosphere of the Earth has left behind oxygen. So we believe that if a planet were to go in front of its star and it has oxygen, which oxygen only exists in Earth at least because of life, it's not stable, and we believe that's probably usually true, we would be able to pick up the fingerprint of oxygen, or quite frankly, some of the crazy things we put in the atmosphere that destroy ozone or something. So it is possible to get the fingerprint of life by making observations, not 100 years in the future, but in the next 5 to 10 as these big telescopes come online. So there's a whole bunch of things to do. So our future as astronomy is very bright. But what's our future as humanity? Well, this kind of tells us that the future of the universe seems to be dark energy. The more space expands, the more dark energy can push against gravity, moving the universe faster and faster. Eventually, the creation of space happens more quickly than light can travel. So imagine a galaxy puts a photon out, space is traveling bigger, it's getting bigger and bigger over time. The photon's trying to get to Earth, but space is being created more and more quickly, and it gets kind of stranded, gets stretched, and the photon never reaches us and just gets stretched to infinity. So galaxies we see in the James Webb Space Telescope images today, the light they emit today will never reach us. Almost everything I showed you in that image, the light that is being emitted from those objects today will never reach us. So unless something happens with dark energy, and I've told you that could be true, unless the dark energy suddenly disappears, the universe at an ever-increasing rate is going to expand, fade away, and so while I have a lot to do now, billions of years in the future, as a cosmologist, I will have nothing to see and therefore nothing to do. Thank you very much. Are we going to take questions? All right, so we can take questions, and Gratzina is going to run around with her microphone for anyone has a question. There is no such thing as a dumb question, but there are questions that are too hard. Those are the ones that I don't like, are the hard questions. But we have someone keen here right in the front. Oh, and we have a box, which is always dangerous. So actually, we'll use the box, then we'll hand it to him afterwards.
Okay.
Yep.
Well, thank you for the nice talk. I wanted to ask a history question.
Sure.
Just before leading to events when the accelerated expansion was discovered, I was wondering what was the main motivation to go and do those observations. So what I have in mind is that probably at that time, I know that it was known that omega m was around 0.2, 0.3.
Yep.
And there was inflation, which predicted it to be 1, the total omega. I was wondering how seriously this was taken, because inflation was already like for 17, 18 years by that time. Did astronomers go there to find missing matter, or just to measure omega m more precisely, or was there something else completely?
Yeah, so it's an interesting motivation. This is one where I'm an observer. So observers had gone through and tried to measure how much mass there was in the universe, and we consistently got there was 20, 25% of the amount of gravity to get us to just right. That was a consistent measure. I was, part of that group. These are my friends. I could see nothing that they had done wrong. My friends who were theorists kept on saying that makes no sense. From a theoretical point of view, that is messy. If we want the universe to have this inflationary period, it really has to create an omega equal 1. That is, everything adds up to 1. But, my view as an observer is theorists all the time, when they can't make sense of your observations, tell the observer you've made a mistake. That's just the way life is, okay? So this was our reaction to this, saying, well, you suckers, we're going to go out and measure this in a completely different way, in a way you cannot argue with. All right. So I had expected we would measure that the universe was slowing down just a little bit. We would definitively measure that, and I would tell the theorist, suck on it, inflation and your ideas of the early universe are wrong. Now, when we measured acceleration, it turned out we had not been thinking that the omega, the stuff that we needed to make the universe flat, wouldn't be normal gravitating matter. It could be something else. So it turned out it allowed inflation to be right. That is, the universe was flat, as predicted by theorists. It created this crazy, the universe is speeding up. Turns out it made the universe about the right age. The universe wasn't quite the right age without this, because when you take the extrapolation, if the universe is even slowing down a bit, instead of being 13.5 billion years old, it's more like 12. We think the oldest stars are older than 12. So there was some problems. So it kind of fixed almost everything, even though it was messy. So to my surprise, in 1998, rather than people throwing rocks at us, which is what I thought was going to happen, the theorists were actually the champions, saying, this has got to be right. And the observers were like, oh, come on, this is crazy. We need to check this. So after a couple years, it became clear that actually it seems to be what the universe is doing. And for a while, before we had the Hubble tension and perhaps universe evolving, its dark energy changing a little bit, we had a nice, clean story. Now the story is getting a little messy again. And that's the way science is. You think you understand it, and then you don't.
Thank you.
Thank you. I wanted to ask regarding the experimental data, especially in the smoking gun experiment that you showed that led you to the idea of inflation, but also in some other data I saw, and maybe you can comment if this is a coincidence or is this a tendency, that there are larger like error bars in the middle range of the time, like the deeper time margins are smaller, and the
it's a real problem, and those errors are the uncertainty in the middle. So if we look back about 2 or 3 billion years, for supernovae, it turns out we have two ways of discovering objects. Great big telescopes looking at a small piece of sky with a big camera on it, and then we can see really, really deep, and we can start picking up objects all the way back to 8, 10 billion years in the past. The problem is they don't look at a big enough volume of the universe to see objects in the nearby universe that are only 1 billion or 2 light years away. The other way we see our little telescopes looking at each galaxy, each nearby galaxy. Well, turns out those telescopes are too small to look and see these objects that are in between. So we have a bunch of objects nearby that are nice and bright. We have the big telescopes looking at the very faint objects, and the ones in between where we need a pretty good sized telescope look at a lot of volume of the universe to find enough objects. We just haven't had the technology. We do now, but we haven't had. So expect us to get a lot of data in that bad spot very soon. For the galaxy experiments, the problem is that if you look at the entire sky, you only, out to 3 billion light years, you only have about 10 million galaxies. And you naturally don't have a great experiment because you just don't have enough galaxies. And the universe only gives you so many galaxies, so the precision of those experiments, it turns out, are really hard to improve because you just don't have enough galaxies to look at. So it turns out we haven't looked at the entire sky. We are going to be looking at the entire sky. We're going to look fainter. So we think we can improve the experiment's precision probably by a factor of 2 or 3 over the next 5 years. And that will help us hopefully break, the question of whether or not this is just a fluctuation or it's a real measurement. That's my hope. But there are reasons why there are gaps there. It's not just us playing bad. One more question? Well, you keep going.
Thank you for a very exciting talk, and in particular, making it accessible to people who are not from the physics department. So you spoke quite a bit about technology, and I think broadly speaking, there are the instruments, telescopes, et cetera, and then there's like the computational side.
Yep.
Could you talk a bit about the sort of the computational advances since you've entered the field? Maybe machine learning, that sort of stuff, and do you think that's actually contributing significantly to the future work in your field or not?
All right, so computation has become from a huge constraint, still a constraint, because when you're going to model, let's say you're going to model the universe, you need billions of particles. And it turns out the bigger the supercomputer, the more particles you can have, and the more physics you can put in to the simulation. So the simulations 25 years ago, quite frankly, they didn't really look like nature. Now they do. Now, you get to tweak the physics, ask the questions, and learn because the computational memory and just processing power has gotten so much better. So it really does allow us to do much better simulations. Astronomy has always been early adopters. I had to find those distant supernovae. I had a 2-layer neural network in 1994 So I was using neural networks before they were cool. Okay, I didn't really know what I was doing, but I was still using them. What I'm seeing now is AI is allowing us to emulate really complex physics computations that we can then speed things up by a million or a billion. So that's how I'm using it. Of course, I use it to, okay, here's a paper, AI, rather than me spend 3 months trying to figure out how to reproduce the thing, I can just, boom, it'll plop out and say, well, here's the code that does what they said. Do you want me to try it, do these tests for you? Yes. So I think it's going to change the speed by which we can do things. I don't think it's going to replace astronomers. It's going to make astronomers much quicker at doing their work. And whether or not we're going to have an AlphaFold moment where we can do something big we've never been able to do, not so clear to me. If, you know, at this point, machine learning still is, as I would describe, as interpretive, okay? That is, where you have information, it is really good at connecting the dots. It is not good, indeed, it's exponentially bad at extrapolation, where it goes beyond where you have information, right? And humans, you know, the Einsteins are Einstein because they extrapolated. They didn't interpolate on what we already knew, they extrapolated. And so I haven't seen evidence that machine learning extrapolates yet. And we could get into a, you know, philosophical discussion on that. I still have not seen evidence that it extrapolates, in physics at least. I think we're learning how to use it. All my students use it, I use it, but we use it to become superpowered rather than it changing. It's certainly not asking the questions, it's certainly not solving the problems, it's helping us solve the problems.
Thank you for saying that I will not be more clever than
Well,
physicists.
not yet. Yes. I have a lot of conversations with students about making sure that they understand that AI is there and machines are there to serve us as humans, not for us to serve them, and to make sure that when they're learning, they think about how they remain in control of the machine, because what will happen is the accountability will lie with the human. And so what will happen if you don't stay on top of this is you're going to end up working for some evil overlord who controls the machines and controls you through the machines, and you don't want to be in that situation. So I'm not saying you want to be the overlord, but ideally we need to rise up and make sure there are no overlords controlling us through the machines. And if you do see your AI acting up and looking like it wants to take over and have accountability itself, unplug the machine first thing. Don't let it go. We don't need a new race of super intelligent beings on this planet. Okay.
Okay, thank you. First of all, wonderful lecture. Can you just comment a bit about Penrose's cyclical cosmological model using conformal geometry? Does it sound persuasive for you? Just a small comment. Thank you.
So someone like me is not going to tell Roger that he's wrong, because Roger's a lot smarter than me on the theoretical side. What I can ask is this what nature looks like? And the answer is no. It's not what nature looks like. So yes, I am happy to tell Roger, keep working on it, but at this point, I don't see what you think is going on in nature. And so he can make it so you can't see it. But theorists are very good at making up theories you cannot test. And so a theory you cannot test is not really a theory. It's something else. It's a meta theory. And it's a real hard thing being a theorist. The really great theorists come up with new ideas you can test. Coming up with ideas you can't test, anyone can do that.
Yes, there could be many people who propose some hypotheses, but real science is what we can test, then we can believe. So I thought to ask, what is your opinion are black holes a part of dark matter?
All right, so are black holes part of dark matter? So there's been a lot of work on this, and I think I can quite definitively say they are not an important part of dark matter because experiments have been done. What do I mean by that? So it turns out that if a black hole, if there were lots of black holes randomly scattered throughout the universe, then they can act. They more or less don't interact with anything. You know, if one comes through the Earth, it goes right through the Earth, puts a little hole through us or a big hole through us, but they would be quite rare. But it turns out they do magnify, they act as a magnifying glass as they go through the universe. And so you can ask, when you look at the galaxy where there are literally billions of stars, you can ask how many times will we see stars magnified based on how many black holes there are and how big they are. So that is an experiment that was done at Mount Stromlo Observatory with a telescope that we sadly burned to the ground in 2003. Our Polish friends nearby have done an even bigger experiment along the same lines. And we can definitively show that the universe does not have enough black holes to actually make up essentially dark matter. Because if we did, we'd see this magnifying thing, or there'd be some other constraints. Now, it could be, and this is quite exciting, one of the things we've seen in the gravitational waves this year is we see things merge, and we saw something merge that looked like a black hole, but had a mass less than the sun. There's no way to make that by any physics we know, except for having that being created in the early universe as what we would call a primordial black hole, something created right after the Big Bang. There can't be very many of them. This, I will say, this measurement we saw is kind of smelly. Most people don't really believe it. So I'm really interested. Are we going to see more of these things? Because if we did, that would give rise to the idea there are primordial black holes, which would be incredibly exciting. But there's no way there can be enough of them to replace dark matter. Dark matter has to be something else.
But it is interesting that small black holes could be primordial. I imagine that large black holes could be formed at the beginning.
Well, at the beginning, it turns out you can make any size black hole if you're a theorist. You can make microscopic ones. So I want you to think of a universe that's full of microscopic black holes that make up the dark matter. Well, then we would be sitting here and we would all have black holes go through our head and we would die, right? It would be like getting a headshot all the time. So you can rule those out because we wouldn't be here, okay? And when you make them too big, it turns out they magnify so much of the universe, you can't miss them. So there's sort of constraints on both sides. Thank you.